Hello guys, welcome back. This will be the fourth video tutorial about peridynamics, and I think this tutorial will be very interesting to you because we will actually be talking about how to really employ the material models that we have been seeing so far, the bond-based and the state-based, in an actual peridynamics code. We will use a tensile example, tensile bar, which will be subject to deformation on both of its sides, and we will see how this can be, how we can post-process these results. But before doing that, please allow me just 5 minutes of your attention to tell you how the peridynamics linear solid material model, the state-based, can be seen in the peridynamics code. So, looking into our previous expression, we said that the state-based peridynamic equation can be specified in terms of the bulk modulus and the shear modulus mu, as in here. So now, rewriting this expression in here and knowing that we have the deviatoric bond extension D defined as the bond extension minus its volumetric part, it will leave you the remaining, the deviatoric part, and substituting this into this, you can have here the bond force if you factorize this term here and this term here, put them inside the brackets as it is here, like factorizing the influence function and theta outside, as well as the x, which is the bond original position, and then putting inside the brackets the 3k over the weighted volume minus, because of this minus here, the parameter 15 mu over the weighted volume and this 3 here, and then putting outside the summing the influence function, again this omega here, the 15 mu over m, and then after calling, you can call this parenthesis parameter here a constant C1, and then also this other constant, the 15 mu over m, we call it alpha. You can end up with this other expression. And why am I showing you this? Because this is actually what you see inside the peridynamics code in Peridigm, which I will show you just in a minute. Like if you have here, if you go here to the source material, then you go to the materials, then you go to the elastic material model, you will see here the computation of the parameter C1, as in here. Yes, and this C1 is exactly omega theta. Well, in this case they put they consider C1 all this term here, which is omega theta 3k over the weighted volume minus, and they call it alpha, this 15 mu over m divided by 3. And then if we just forget for one moment about the bond damage, which is something that we are not actually looking into this moment, we will see that this whole expression called C1 is multiplying the bond original position zeta, which is x for our case, and then summing the omega here again, the alpha, which what we said that it is the 15 mu over m, and then the bond extension E. And here you see that alpha, as we said, this is a constant, and it is defined here as 15 times mu over the weighted volume m. So why am I showing you this? Because sometimes people tend to confuse that they see in the peridynamics code, they don't see this expression as it is here, but in fact it is the same as the one that is coded inside Peridigm, because after doing these simplifications. So now, going into the other part that interests us is the simulation of the tensile performing a tensile test actually with the Peridynamics code. And for this, we will be employing the Linear Peridynamic Solid, and we will be employing two material properties, which is the bulk modulus of 1.5 times to the 10 times to the 12 pascals, and the shear modulus here, and which, if we consider these expressions, this is exactly the same as having a Poisson ratio of 0.3. Yes, and the example will have 12,625 particles. So now, looking into our exercise, for that we will actually be using the first example that is provided inside the Peridynamics code, which is, if you go here to the folder examples, you will see here the tensile test. Yes, and this is exactly the exercise that we will be working on. So for doing this, we can see here we are exactly in this folder, which contains the same files. And here, interestingly, the most important files for us will be the tensile test.g, which contains the material geometry, and the tensile test.peridigm, which contains the input material parameter input file that we will be using so that Peridigm solves what we are asking for. So what do I mean by that? If we open this tensile code Peridigm, we will see information regarding the divided by section concerning the discretization, which input geometry we are employing, which is the file that I showed you before, the materials considered, the same information considering the blocks and the geometry, how it is being divided into different blocks which employ this material, which have this horizon, this in which we will be employing these boundary conditions, and we will be prescribing certain boundary conditions on specific node sets. And here it is speaking about the solver, which we will be employing. In this case will be a quasi-static simulation in which the final time, the time in this case, it doesn't really matter, but in this case the load will be applied using 4 time steps. This means that the whole load 1 will be divided by 4, 0.25, then 0.5, 0.75, and then 1. Finally reaches 1, and then the simulation finishes. Then some computing class parameters and some output that we are asking for our simulation to obtain from. Yeah, but this, I wanted to show you that this is actually a deprecated format, and for this reason I prefer to use the .xml extension, which is a more updated version. So I have it here open, and this, if you go through this list, this will represent exactly the same as we were mentioning previously as here, just with the difference that this is another format. Why I prefer to use this? Well, as I told you, because this is not a deprecated format as it is the other. So, but these both can be employed and both will provide you the same results, because this is just the way to interact of your in order to tell Peridigm what you want him to do for your simulation. So exactly this. So now if we look at the geometry, and we can open it by this file here, we will see here that this consists of a finite, this will be a finite mesh geometry that was created with some external measure. We will not speak about this for this moment, but I will show you later how you can create all these geometries, of course. And here the interesting part is that you will see the material that has actually elements, right? You see elements, but we said that in Peridynamics we are employing particles. So what's happening here? And here the reason is quite simple. Peridigm, what it will do, it will convert the elements into particles while searching and analyzing this geometry. Yes. So how is it going to be happening? Well, in each position where the centroid of each element is located, it will place a particle instead with a specific radius. And this radius of this particle will occupy a volume, and the volume will be exactly the same as the current particle element, size. Yes. So let's say if this element had 1 cubic meter of volume, then the same particle would be placed exactly in the same position of having the same volume. Yes. So now, looking around into this input file, I will show you now that here we are defining in the discretization part, our input geometry. Here we are defining the material that we will be interested in employing, which in this case we call it elastic, and Peridigm also recognize elastic, but this associates it with the linear peridynamic solid, which is the state-based material that I was showing you in the previous slides. So we are inputting the material properties that we saw earlier, and in this case we are using standard international units, which are pascals. That's why it's e to the 12 pascals or e to the 11 pascals. The density, we are also setting it here, and we have something that is called blocks. And what are these blocks in here? Well, these blocks, I will show you that in a minute. They are just exactly these ones here. So as you can see here, we are specifying 3 blocks, and these 3 blocks, if we click on the first one, this will be one extreme of our bar, then the block 3 will be the other extreme of the bar, and then the middle block, the block number 2, is the bar itself. So in this case, the geometry has been divided into 3 different blocks. And why the geometry is being divided into these 3 blocks? Because this way you can specify a different material model to each of these blocks. But in this case, since we are going to be analyzing everything with the same material model, we are putting them all the 3 of them inside the same. Yes. This simulation type, you don't have to worry in this moment about that, because in fact this is something that is that I added personally, which this means that it's working in 3 dimensions. But if you use the standard peridynamic model, peridynamics code, you don't need to specify that yet. Okay. Now, in here, you specify the material model, which is the linear peridynamic solid I mentioned to you, and you can specify a different horizon on each block. So let's say this horizon, remember, this is the interaction of one specific, let's say, particle with all the rest. So you can specify this size of interaction, which in this case we are specifying at 0.16 meters. Okay. And what are these meters? Let's have a look into, if we look here into the size of one element, we can put here ruler and then type the keyboard P and then the other P. It will provide you more or less the size, which is 0.06 meters. Yes. So in this case, we have specified that our mesh is 0.16. Yes. So 0.16 between 0.06, it more or less has an approximate approximately 3 cell cubes of interaction, meaning that each of our elements here are of our particles instead will be interacting with other 3 elements around this around the center position of each of the element, right? Each of them will be interacting with 3 to the right, 3 to the left, 3 to the in diagonal, 3 to in the depth, and so on. But since we are considering a sphere, so more or less the size is approximately 3 particles. Okay, well, anyway, let's continue. So if we see here, we can, if we go further, we can see here in this section the boundary conditions. And what are the boundary conditions? This is where you will specify the subject strain that you want to apply to this specimen, which in this case we want to stretch it 0.5%, and we want to stretch it 0.5% in here and in here. So the meaning in this direction, which we see here the y direction and the y direction. And this is what is trying to being specified in this part, because we are prescribing a displacement in the node list 1, and we can see here which one is the node list 1 by going here. If we click on the node list 1, oh, it's not very well seen, but we can put here surface, and then you will see the node list 1 is exactly this, all the particles that belong to this block on this left-hand side. Then they are being applied a stretch in the y direction, in the coordinate y, and the value that is being applied is being stretched in a ramping way. And when I say ramping, it's because it's time dependent, and as you can see here, it is applied the y position times multiplying by 0.0055 in the strain. And why is this? Because if we look where is the current position of this material, we can go here to probe location. Then we can see that the center is, in fact, let's put it located in here. Yeah, the center in the y direction is exactly located in the middle here. Yes. So if we say that this is going to be stretching in the y direction, which is this current position y multiplied by 0.005, this is why it is being applied a 0.5% stretch in with respect to its current position in y, which in this case its current position in y will be negative. Let's say these points here will be -3 or -2. Let's assume that for a moment, but they will be definitely negative. And in this part, they will be positive. So if you apply here a negative times 0.005, then it will stretch in that direction. Whereas in this case, the node list 2, you can see it here. It is going to be this part, and this is going to be stretching in the opposite direction, the 0.5%. But this will be applied in steps, and this is why it is being multiplied by time, which is time dependent. Okay, so now these other node lists 3, 4, 5, and 6. Let's see what are those. If you look the node list 3, it's just this corner, and the node list 4 is just this corner here. These positions are just being fixed in the x and in the z direction, and the same goes for the node list 5 and the node list 6, which are in the opposite geometry, which are here. All these nodes in here, they are just being fixed. And this, why is this done? It's just to ensure that the deformation is going to be axial and not on the, and there won't be any type of rotation or any other deformation in any other action, meaning that this will only require a stretch. Okay, now going into the second part here, we have here the solver, in which we are specifying the final time t of 1 second, and this time will be separated into 4 different load steps. So meaning during one load step it will apply up to 0.25, then on the second time step, on the second load it will apply until time 0.5, then until time 0.75, and finally until time 1. That's why it's being divided by 4 here. The absolute tolerance, this is just to make sure that the residual of the peridynamic equation gets to a value of less than 1, and then if this result is achieved, then it will go to the next step and so on. More information I can show you, I can tell you later but for the moment I think it's okay. So this means, this is why we have here in the applied displacement, we have here that is going to apply only 25% first, then 50%, then 75% until it reaches the final strain of 0.5 here when this is equal to 1, when t is equal to 1. And here on the next part here, it's just some computation parameters that we will not be looking for the moment. We will not be explaining this in this moment, but something interesting to compute here, as I would like here to show you, it's just the weighted volume and the dilatation function that can be seen here. The dilatation here and the weighted volume, not only the force values, which we have already specified in here, the force density or the force here, but also we want to see the weighted volume and the dilatation. So now, in order to run this simulation, this is quite simple. The only thing you need to do, it's I will create just this another folder here, make dir elastic. I will copy inside our input file on our input geometry. Then if I go to this folder, you will see here, and then I just need to click to type this here, and this will start computing the simulation. As you can see here, these are just requested parameters that are needed here, and this is allocating a global tangent matrix because this is a quasi-static solution of a problem. And I'm not going to let it run completely because it's going to take a while, but I can show you that if you let it run, you will see this is what we see already, and you will see all the simulation finishing as in here. Where important things here are this table, in which it will tell you the total time that it took in seconds, and some other parameters which are not really important in this moment to understand for the simulation. But I will cancel this. But if I go back, which I see here all the results, and then I open here the tensile test.e, which is the output file, we will see all the computed fields that we asked during in our input file. Let's activate all of them, apply, and interestingly, we don't see any more elements. We see now particles, but these are so small that you cannot perhaps identify very easily. So that's why I'm going to be using here a glyph, which is a filter in order to convert all the points here to actually spheres which have a bigger radius. Let's put it like this. Okay, 0.1 is too few. Let's try 0.5. Okay. And here, wait 1 second. Let's put scale, no scale on any way here. Let's convert all the points. Okay. Okay. Let's put, this was too much. 0.1 again. Okay, 0.1 is working much better. But in order for you to really understand how these are really particles, you see, now it's beginning to see the particles instead of the elements. So let's put it 0.025 here. Okay, so here is the interesting thing. Before we had here elements, but now you see all in the place inside, instead of the elements, we can see here now particles. And this is what we are actually looking at in this moment. So, and these particles, each of these particles possess the same volume as the previous element. Yeah. So here we have, now if we want to see the deformation, we can go here and show us the displacement. Okay. This was the time 0, then this is the displacement on the time, on the last time step. It's taking some time to compute, but here it is. And you can see here how it was stretched from this position, which was the original position, and then it stretched to the final position, where you can see here the 0.5% being applied in each of the 4 time steps. So you have in here it applied only 25% of the stretch, in here applied 50% of the stretch, and then in here 75% of the stretch, and then finally it reached to the 0.5%, which corresponds to the 100% of the stretch, initial stretch. So I think this will be enough for today's session. On our next session, we will talk about how you can employ a different material model. We will continue post-processing these results. So please, I hope you did like and enjoy this video. If you did, please give it a like and subscribe to my channel, and see you next time. All right.